I'll show you different techniques that you can use to make your application scalable, all the way from the front-end services to the back-end database. We will look at topics like partitioning, sharding, caching, using content delivery networks, and managing APIs, all while leveraging features in Azure that make scaling easier. Performance and scalability are two terms that go hand in hand, but they do have different meanings. When we talk about the performance of a cloud system, we are generally talking about the responsiveness of the system during a single request. How long does it take for the home page of your application to load? How long does it take a command to pass through a queue and update a database? Scalability, on the other hand, is talking about how your system responds under the load of many requests. Can your system handle 1,000 concurrent users? Can your system handle 100,000 concurrent users? Does your system work as well with 1 terabyte of data as it did last year when there was only 1 gigabyte of data? The goal of being scalable is to handle your peak load without losing performance. So we're going to focus on scalability in this module, but the business value we are delivering is performance. Even under load, we want our customers to have a responsive system. Let's look at the type of architecture one might use for a scalable system. Every application has some unique requirements, so what I'm about to show you might not work for your application, but I want to describe a generalized architecture that you might see in the cloud. It all starts with our customers who want to reach our application. They might be using browsers, they might be using mobile devices, but all the traffic arrives at the system over secure HTTP. For a scalable system, we'll have a load balancer in place, and that load balancer might be Azure Traffic Manager, which we saw in the last module. Traffic Manager allows me to handle load by distributing requests across multiple app service deployments. And the app service deployments themselves can use auto-scaling to scale out when under load. I showed you how to set that up in the Getting Started course. So with Traffic Manager in place in front of our application, not only would the system be more resilient to failure, the system would also be prepared to handle more load. There's another Azure resource that we can also place in front of our application, and that is an API gateway. We will look at API Gateway in more detail in this module. For a brief introduction, I can tell you that API Gateway can help us manage the API endpoints in our application and allow me to secure, optimize, and scale those endpoints. Again, more details in this module. Yet another resource we can leverage in front of our app service is the Azure Content Delivery Network, the CDN. We will also look at the Azure CDN in this module and see how we can offload static content from an application and cache the content on Azure servers around the world. For the back end of our system, let's assume the system is using blob storage and perhaps other features of Azure Storage. Scalability with Azure Storage revolves around partitioning your data, which we will look at in this module. Of course, the system probably requires some data persistence too, and maybe the system is applying the Command Query Responsibility Segregation pattern, CQRS, which we touched on briefly in the last module, but CQRS simply means the system uses one approach to reading data and a different approach to writing data. Perhaps operations that require a database update will send a command as a message to a service bus queue or even a topic. With service bus, you can also scale using partitioning. And then on the other side of the queue, perhaps you have a Windows service running on a VM to process these queue messages, or maybe you process them using web jobs or Azure Functions. Functions provide an easy scalability model as functions are serverless, and Azure will assign the resources needed to match the load on the functions. And ultimately, the backend processing will update or insert data into a database like Cosmos DB or Azure SQL. Both of these technologies also support data partitioning to achieve large scale. In case you haven't noticed, partitioning is important for large data and large systems. What about read operations from the application? Here we can use an Azure Redis cache to improve performance and scalability. I'll give you a demo of Redis in this module. And finally, to build a high-performing and scalable system, you're going to need good monitoring and instrumentation to understand how the system is performing and locate bottlenecks. For this, we can use Application Insights, as I showed in the Getting Started course. App Insights can give us a tremendous amount of information about how the application is behaving. So with this sort of architecture in mind, let's start with the backend and work forward as we discuss scalability topics. In our backend storage, we typically use partitioning to achieve scale, so let's get started with a partitioning discussion. The data storage for a software system can often be a bottleneck. If you try to run an application using a single database server, as you scale, you'll soon reach the limits of a single machine, even as you pay for a bigger, more expensive machine with more CPUs and memory. This is where data partitioning can help. Here's a simple example. A block blob in Azure Storage currently has a maximum size of just under 5 terabytes. 5 terabytes is a large blob, but what if you have 8 terabytes of data to store? Well, you'd need to partition your data across multiple blobs. You could, for example, store 4 terabytes in blob 1 and another 4 terabytes in blob 2. That's a simple example of partitioning. Now, let's talk about 3 specific types of partitioning. First, imagine you need to store orders in your application, and an order consists of 5 attributes. We'll just call them A, B, C, D, and E. These attributes could be columns in a relational database or properties in a document-oriented database. But let's also say that the application frequently accesses attributes A and D, but rarely accesses B, C, and E. In that scenario, we can vertically partition orders so that A and D are stored separately from B, C, and E. This could have a few benefits. For example, there could be less contention in a database if the attributes are separate and the tables are not as wide. Or we could store A and D in fast premium storage, while B, C, and E stay in less expensive cold storage. Also, A and D would be less information and easier to cache and faster to replicate, so there are several opportunities when using vertical partitioning to optimize your data. Another approach with orders is to spread the order data across multiple data sources. This is what we call horizontal partitioning, and horizontal partitioning is a popular approach to scaling data because this approach gives you a lot of power that you can use for scalability and performance. One approach to horizontal partitioning is to use what we call range partitioning. I could say that all the orders for customers A through M go to one database, while all the orders for customers N through Z go to a different database. A range could also be temporal, so I could say all the orders for this month go to one database, and all the orders for last month go to a different database. Or I could have a hashing algorithm that places orders into different databases in a more round-robin fashion. You can almost think of it like load balancing for databases. The choice here really depends on the application and the data and how the data is used, but in a horizontal partition, I use the same schema or same document shape in all the different databases, but since I'm spreading the data out, it's easier to scale out my hardware and add more processing power as my data grows. Finally, there's also what we call functional partitioning. Let's say for this scenario, our system stores orders and also stores invoices. In functional partitioning, these two data sets could live in different data sources that are optimized for the data and the system that uses the data. So we could use a relational database for orders and a document-based database for invoices. This sounds complicated, which is true. You don't necessarily want to use functional partitioning for a simple application. But for large systems, for large data, for a scalable system, functional partitioning is one partitioning strategy to evaluate so you can match up the best data store for your data and application data access patterns. So I cannot tell you which partitioning strategy is best for your application. I can just tell you that if you need to be highly scalable, you should evaluate a partitioning strategy, and yes, partitioning can complicate your design and implementation. It can be difficult, for example, to join data across partitions or enforce transactions across partitions. We'll come back and talk about that in just a bit. For now, let's look at a specific Azure resource and see how to achieve partitioning.